Hello, ladies and gentlemen, and welcome back. Root Beer here, and we are at the very last question of our grade 11 Fermat contest. This is the Fermat from the year 2018. So we're at question number 25. If you haven't tried this question, feel free to get a copy of the contest down below. You can print it out. It's a little late to maybe try some of the other questions, unless you just skipped right to the end. But I do encourage you to actually try the question out on your own before reading the solutions they have posted online or watching me go through and develop my solution. Just because you get more practice that way. Anyways, here we go. Question number 25. For each positive digit d and positive integer k, so I guess digit d they mean 1 through 9, and positive integer k, we use the symbol d and then k in brackets to represent the positive integer having exactly k digits, each of which is d. So just repeated digits, I guess. So 2, 1 is 2, because 2 is repeated 1 time. 3, 4 is 3 repeated 4 times. Okay. There are n quadruples p, q, r, k, with p, q, and r positive digits, so no zeros. K a positive integer with k less than or equal to 2018. And p repeated 2k times minus q repeated k times is equal to r repeated k times squared. The sum of the digits of n is... Okay. They really like these sum of the digits of a counting problem question, because I feel like there's been a couple in the 2018 year. Okay, so we need to figure out the number of quadruples. Alright. So the first thing I would probably notice is the numbers that they're talking about, like 3, 4 is 3, 3, 3, 3, 3. That's really 3 times however many ones you need. Okay, so dk is d times, and then some number of ones, specifically k ones. Okay, so you can play around with it a little bit. Now, if you've seen numbers like these before, you might say, well, is there a way to express this neatly in terms of k? Because what I'd like is an expression that I can actually work with rather than this, which I symbolically understand, but I can't really do computations with. Okay, and if I have 1 1 or 2 1s or 3 1s, or as we have up here 4 1s, and I multiply that by 9, I predictably get a bunch of 9s. And that's always 1 less than a power of 10. Now, which power of 10 and how does it relate to the number of 1s? Well, if you want 3 1s, 1,000, well, that's 10 to the 3. So I guess we can write d times 10 to the k minus 1 all over 9. So this is now an expression we can use. And p2k minus qk equals rk squared can now turn into p 10 to the 2k minus 1 over 9 minus q 10 to the k minus 1 over 9. And that's equal to r 10 to the k minus 1 over 9, and that's all squared. So that would be r squared 10 to the 2k minus 2 10 to the k plus 1 all over 81. Okay, so this is an actual equation that we can work with, that we can manipulate. Now, we still have the constraints that p, q, and r are single digits, but and I think we can clean up a little bit. But I'd say this is progress of a kind. We've taken their notation, perfectly fine notation, but it was nice for symbolic reasons. But there was no actual, like, the equal sign didn't really have meaning. You're saying these two expressions are the same, but I'm not able to manipulate it. Now I can. So, for example, I don't like fractions. I make no secret of that. So I'm just going to multiply everything through by 81, get rid of these fractions here. And so we divide by 9, so we'll get 9p 10 to the 2k minus 1. I'm keeping my eye on that 10 to the 2k because it's in both sides. And it's minus 9. So we could even factor 9 out here. 10 to the k minus 1 And that's equal to r squared 10 to the 2k minus 2 times 10 to the k plus 1. Which, I guess actually we could... So I'm going to pull a 9 out of here. I'm also going to be able to pull a 10k minus 1 out of here, because that's a difference of squares right here. And so that'll leave me with p 10 to the k plus 1 minus just q, and that's r squared, and this was 10 to the k minus 1 squared. So I guess I didn't need to expand that out. Now k is a positive number, so these are not going to be non-zero, so the first thing I can now do is cancel out one of these on either side. So that's nice and neat. And then 10 to the k plus 1 minus q is r squared 10 to the k minus 1. Okay. Is there anything more we can do from here? Or should I just start guessing and checking and things like that? Because I don't really have any of these variables isolated. Now I could expand and get 9q and get that in terms of a square and things like that. So that might be something to look into. Not entirely sure what we might want to do from here. I don't want to... I really don't like this 9 over here. And it keeps screaming at me, divide it by 9. But we're trying to avoid that. We're trying to simplify. I'd like to get just some p's and q's all by themselves. Now, I guess one thing we could do... Because we got powers of 10 here. So I suppose we could write this as 9p 10 to the k plus 9p minus 9q is equal to r squared 10 to the k minus r squared. And what's going on here, sort of, is these 10 to the k's. Now, if we're talking about really, really big numbers, and it might not even have to be that big, but if something like k is greater than 5, the fact that these are single digits is really going to play a particular role, because let's say k is 5, p is, I don't know, 2, and q is 5, and r is, I don't know, 6. If this works out, this will be a miracle, but I very much doubt it. But the point is, look what's going to happen. So we'll get 9 times, oh gosh, what did I say they were? 2, 5, 6. I should have just said something like 2, 3, 5. But I was just trying to be random. To the power of 5 plus 9 times 2 minus 9 times... I guess maybe I should make q smaller than p. So we'll make it 1 just so the math works out, and r is 6. And so then we get 6 squared times 10 to the 5 minus 6 squared. Okay. Or actually, maybe it should have been 5. Maybe it should be 5. But the point is, this will be 18. Well, not even 18,000, but 1.8 million. And over here, you'll get 33.6 million. These parts here will sort of have to match up. So I guess if I wanted to sort of revise this and make it look a little nicer and neater, we might say something like 4 here. And that would make the 36 match up here. And then you're still going to have some subtractions here. Certainly, I guess if we make this 8, we would get minus 36 and minus 36 here. Now, this isn't about me working an example so that it works, although this is interesting to note that I guess 4, 8, and 6 will work. but it's more about the fact that these two parts will have to match up just because the powers of 10 are taking them away so much that subtracting... I mean, this expression here is at most something like negative 162 if they were both not... Actually, no, if one was 0 and one were 9, this is at most 81. And this thing here is at most 81. Okay? So, what can we say from there? So, we've got a big power of 10 here, and that's sort of, you're treating it almost like it's the digits in this place, and then you're comparing the digits in the single and second digit places, I guess is what I'm trying to say. Now, can I actually write that down in a better way? So we've got 9p 10 to the k plus 9p minus 9q is equal to r squared 10 to the k minus r squared. So if I bring that over to one side, 9p minus r squared 10 to the k is the same as 9q minus 9p minus r squared. These two have to be equal. But if 9p is not the same as r squared, that is, if I don't get a 0 here, and k is big enough, then actually here let's write this out a little bit better. So let's focus on the right hand side. 9q minus 9p minus r squared is at most 9 times 9 minus 9 times 1 minus 1 squared. That's the biggest we can make it, making p and r as small as possible, making q as big as possible. So this is at most 71. And it is at least, so making q as small as possible and p and r as big as possible, it is at least 9 minus 81 minus 81. So that'll be negative 153. Okay. So minus 161 plus 9. So there's quite a limited range, and if I have 9p minus qr squared, if that's anything but 0, then suddenly I'm multiplying something as... So this is at least 1. Well, if I make k bigger than 3, actually bigger than or equal to 3, we'll get 9p minus r squared is times 10 to the k is bigger than 1,000, and or 9p minus r squared is at most negative 1, in which case then 9p minus r squared times 10 to the k is lower than 10,000, or lower than negative 1,000, which clearly can't match up with numbers in this range. Okay, so I guess if k is greater than or equal to 3, we have to have (9p minus r squared) equal to 0. If not, it's too big and the powers of 10 sort of screw things up. And that's really nice because oftentimes I've found the more recent sort of trend is that you have a lot of casework when you're doing things like the last Cayley or the last couple Fermat questions. And even Euclid questions are starting to get infected by this. Well, infected is kind of a mean term. If you like casework, that's fine. But it's sort of like the prevailing notion, like back in the... I think late 70s, there were a lot of geometry problems. Like Archimedes' broken chord theorem. I remember that one popping up at one point. Anyway, this is not about contest history, but the point is casework is sort of something I start expecting in these late 2010 papers. So we've identified some casework, and we've sort of split it up into k greater than or equal to 3. So from 3 up to 2018, we're going to do one thing, and then we'll just have, well, what if k is 1 and what if k is 2? And that should maybe add some cases as well. Okay? So that's our thought here. Anyway, getting back to it, let's take a look at this case because it sort of presented itself. Well, if this is the case, then I guess 9p is equal to r squared. And so this is 3 squared times p is equal to r squared. So p is a square. But it's a single digit, so p is 1, 4, or 9. And that would make r 3, 6, 9 as well. Okay. So these are our possibilities. So we've got, I guess, 3 cases. Can we find a q that makes this work? So we also need, what is it? 9q minus 9p. The other side of the equation has to be equal to 0 as well. But now we can just try these. So if p is 1, 4, or 9, we get 3, 6, and 9, then I guess 9q has to be equal to 9p plus r squared. So that would be 9 plus 9, or 36 plus 36. Oh, because it's going to be the same number. So 72. So 9q has to be 72, or 18, or 160, or 162. So that would be 81 plus 81. And dividing by 9, we'd get q is 2, 8, or that's going to be too big, because that's 18. So, for k it's up to and including 2018, right? Yeah, less than or equal. Okay, good. Got to make sure. So we have 2 cases. P could be 1, Q could be 2, and R could be 3. Or P could be 4, R can be 6, and what was it? 8. Okay. And now is a good time to perhaps double check with our calculator what we've got going on here. So I could pick something like, well, let's just take the 3 example, although we could do something a little bigger. So if I do 4, 2 times 3, so 4 6 times, and subtract off 8 listed 3 times, so 888, I should, when I hit the square root button, get 666, and I do. Fantastic. And I could check the other one, but I'm really confident in the math, because it hasn't been crazy arithmetic. There hasn't been really an arithmetic challenge. So 2 cases, and then 2018 minus 3 plus 1 is 2015 plus 1, so 2016. So 2 cases for each of these 2016 possible k values is 4032. Okay. So that does well there. And, alright, so we've got to move into the other ones. So let's say, how about our case k equals 2? So if k is equal to 2, I can't guarantee that those powers of 10 sort of lift things out of there. And so we're just going back and looking at this equation right here. But now I know k is going to specifically be 2. So 9p minus r squared times 100 has to be equal to 9q minus 9p minus r squared. Okay. So, what can we do here? I'm wondering should I focus on the 9s? Should I rearrange this again? What could 9p... Well, okay, 9p... P could be 1, 2, 3, 4, 5, 6, 7, 8, or 9. And I could figure out 9p, but then r squared, will that be of any use. Also, incidentally, there's nothing that says these other two cases won't work for just k being greater than or equal to 1, right? So I guess, well, let me just do a quick double check on my calculator, but I'm pretty sure if I do 44 minus 8, yeah, that's 6 squared. So we get 2 cases there. So I'm not really breaking it up. I don't know whether or not. I'm going to leave it like this, just so I'm very clear when I read off my k equals 2 solutions. I'm not double counting. It's just a choice we have to make. If you want to do 1 less than or equal to k and get 4,036 cases, but then if they pop up in the k equals 2 stuff, ignore them, that's fine too. Just as long as you don't double count, because I suspect there might be answers here that are designed to take into account somebody double counting. Okay. I'm really thinking r squared is going to be bigger, so I might just want to rewrite this like this, just because I keep feeling like it's negative numbers. It's not a big deal, but it is definitely something I want to look at. Okay. Also, these powers of 9, or not powers of 9, multiples of 9 make me feel like r squared minus r squared times 99, that brings the r squared over to the other side, is equal to 9. So it's 909? Yeah, 9 times 101p minus q. Now I'm going to divide by 9 on both sides and get 11r squared is equal to... This had to be true from the 100, so this isn't something I can now take and apply to other cases. But divided by 9, we get a little something like this. Okay, this is something I can work with now, because there's only so many possible values for r. 1, 2, 3, 4, 5, 6, 7, 8, 9. Only so many possible values for 11r squared. So it would be 11. And then we're just going to see, is it close to 101 or 202 or something like that. So this would be 44, 99, 176. 25 times 11 would be 275. Oh, that could have been a disaster. 396, 49 times 11, 539. I don't want to try and carry these in my head, so I'm just going to bust out the calculator. 64 times 11, 704, and then 81 times 11. That should be 891. Okay, which of these are close-ish to a multiple of 101? Well, this is out, this is out. Now, this one is close. This is 101 minus 2. This one's out. You'd have to be within 9. I'd have to be able to add 9. And so maybe that's a more systematic way to do it, just so that my chart is more exact. And I don't, when I go back to review, I don't feel like I'm missing anything. So 11r squared plus 9 would be 20. 53, 108. It'll end in a 5, so 185. 284. Here's another one that's going to work. So add on 4 and then 5, so 405. Ends in an 8. Carry the 1, so that'd be 548. So that one's out. 713. Yeah, 707's in that range, so that works out. And then 900, so just falls short. So no, no, yes, no, no, yes, no, yes, no. So here we can have PQR could be, the R is 3, the P is 101 minus 2 gives me 99. And that is something we already had dealt with. Okay. Well, not that we had already dealt with, but you could have already dealt with if you'd turned this into a 1. But we didn't. We're leaving it as is, so this is a new case. This is something we hadn't covered yet. Okay, R is 6, and then P is 4, and 8. So another one that we could have predicted, let's say. But now here we go, 707, R is 8, and 707 minus 3, and I'm just going to double check. 4 7s minus 2 3s, square root that, is indeed 88. Okay, so that's 3 more. So what's our total? 4032 plus 3 more is 4035. That is our current running tally. All right, now what happens if k is equal to 1? So this is the last case. So I'd expect maybe 2 or 3 more from here. But what are we looking at? We're looking at, I'm just going to write it as r squared minus 9p so I don't have to rearrange it again. This times 10 is equal to r squared plus 9p minus 9q. I think we can do the same thing again, say 9r squared is equal to 9, and then we'll have 11p, 10 of them plus another 1, minus q. Divide by 9 on both sides, r squared needs to be equal to 11p minus q, and this is going to happen a lot more. But we can set up basically the exact same chart, 1, 2, 3, 4, 5, 6, and preventing any major hiccups, I'd like to say this is actually not a bad question. I think it might be a little longer if it takes a while to realize how to write 1, 1, 1, 1, 1 in terms of something you can use. But I'm going to stop talking there and not count my chickens before they're hatched. Okay, so what is it? R squared plus 9. If we've got an 11 in this range, that's good. So it won't work for 1, but 13, 18, 25, these are all looking good. 34, 45, 58, 73, and 90. So what are we going to make 11p? Well, not going to work out. 11p will be the 11 here. It'll be the 11 here. It'll be 22 here. It'll be 33 here. 44, 55, 66 will work, and 88 will work. So I can figure out P is 1, 1, 2, 3, 4, 5, 6, and then we jump up to 8. And the corresponding Q, we need to subtract off 7, 2, 6, 33 minus 8, and this one should be 44 minus 8, because there's our 486 again. 55 minus 6 is 49, 66 minus 2, and then 88 minus 7. So just adding them all up, we have, so for k greater than or equal to 3, we have 1, 2, 3 works out, and 4, 8, 6 works out. For k equals 2, we have these guys again, but we also had another one, 7, 4, and 8. And now for k equals 1, we have a whole bunch of them. Basically everything other than r equals 1 gives you 1, so that's 8, and we could answer the question quite quickly there, and I suspect there probably will be a time crunch, but there isn't a time crunch on me right now, so I'm actually just going to list them out. So r could be 2, 3, 4, 5, 6, 7, or 8. It's 1, 1, 2, 3, 4, 5. Now something has gone wrong. Oh, I haven't listed the last one. 5, 6, and then it jumps up to 8. Alright, so it was 7. I think this one was 7. The one with 66 was 2. This one was 8. 44 minus 8 is 36. 1, 2, and 3 again. 2, 6, and 4. And then 55 minus 6 was 7. And there we go. So that's 8 of these ones, 3 of these ones, and then 4032 of these ones. So that's a total of 4035 plus another 8 is 4043. Okay, so they don't just want n. Okay, they want, I think it was the sum of the digits of n, right? The sum of the digits of n is, okay, so then it's 4, oops, pressed the wrong button. So then it's, we want 4 plus 0 plus 4 plus 3, so that's an answer of 11, and we just flip back. Is 11 one of our possible answers? Otherwise, we have likely missed a case or something like that. I've got to scroll back up. There he is. And so 11 is, right in the middle. It's C, so that's a fantastic way to end the contest. I'll just bubble in C there. Okay, well, not bubble in, but I like writing it down. But there we go. So that finishes off question number 25. The whole contest is done. I thought that was a fairly reasonable question for our Fermat paper from 2018. I think it was a little better than the 2017 one, if I recall correctly. But oh well. You might disagree. You might have loved the 2017 one and really disliked this one. But this certainly had casework, and if you're sort of tired of casework, that's not the best. But it wasn't bad casework. It was, you sort of had to use the powers of 10 to say, well, let's just split it up into all these ones that aren't going to be interesting and a couple that still are, just 1 and 2. And all things considered, I don't think that was too much casework. Okay, so that's the 2018 Fermat. The 2018 Hypatia is another grade 11 contest you might be interested in, but it's a written contest. So a lot of the writing I do will now actually count for marks and that sort of thing. So you can look for that. The next level up would be the Euclid from 2018, so you can look for that. And of course, I have past Fermats as well all over my channel, and I guess the next Fermat would be the 2019 one. Okay, so someday we'll get into that one. But thank you guys for watching. I hope you have a wonderful day. Feel free to like or subscribe or any of that stuff just to be kept up to date for whenever I post Hypatias or Euclids or more Fermat papers. But have yourself a wonderful day, and sincerely, take care.